Hello everyone, welcome back to Technologies Discussion channel. For this video, I'd like to continue the discussion on filter design. My first portion of this video, I will explain what is actually a transfer function for a filter. So in short, transfer function actually so-called explain the relationship of input and output. This is actually essential for filter design. For example, after the filter, some of the signal will probably need to be passed, some of the signal will probably need to be attenuated. So therefore, with transfer function, we are able to describe them in a mathematical way. So this will be the first objective of this video. Next, I will explain what is actually poles and also zeros and also the frequency response of the filter design. So all this will be the objective of this video. Guys, this is my email. If you have any question regards on this discussion, please drop me an email. Okay, or if not, I actually prefer you guys to ask me your question through the comment. Before I continue, I'd like to urge you guys to help me by like this video. Guys, it's free and it's just a few seconds. Help me press the like button now. For those who are new to this channel, and if you want to support me, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. The design of filter, in fact, involve very detailed consideration of input and output relationship. This diagram here shows the filter here. Basically, this is actually the input of the filter. This will be the output of the filter. A transfer function, okay, which is over here, they basically use to demonstrate how the equation actually describe the output over the input relationship of filter. And hence, because of this, we can actually directly write in a mathematical expression. Why this is important? Because at the output of the filter, we actually want certain response. For example, we want the output amplitude versus the frequency curve to have some desired shape, whether it is actually a low pass, high pass, or band pass filter. So in order to achieve this, we require the filter to either to pass or attenuate the input signal so as to achieve the final desired shape at the output of the filter. Okay, so in continuous time domain, okay, it is defined in the Laplace domain as the ratio of the output signal. Okay, so basically this is actually the output signal ys over the input signal, which is cross s, which is over here. So basically this is actually the transfer function hs. When a voltage is applied to the input of the filter, as you can see from here, this is actually a voltage source. When they are actually applied at the input of the filter, a transfer function Hs basically will be equivalent to V out over V in. So basically will be equals to V out over V in. S being in general a very complex mathematical operator. So basically S means that they have a function of both real and imaginary part. So basically in short, this is known as the Laplace operator. In this text here, S will be equal to steady state sinusoidal equivalent JW. So let's take a look on this here. The magnitude of this complex transfer function is actually referred as the amplitude response. As I mentioned earlier on, this JW includes both the real term and the imaginary term. The real term will be the amplitude response, while the imaginary term will be the phase of the complex transfer function. The transfer function can be expressed as the ratio of two polynomials. So basically this ns is the numerator and the ds is the denominator. So basically this is actually the transfer function. You can see that ns, which is the numerator divided by the denominator. So the roots of the polynomial in the denominator ds are referred as pole. So basically this is actually known as the pole, while the roots of ns, which are located in the numerator, they are in fact referred as zero. Okay, so the order of the filter is actually the largest exponential of S in the polynomial. Okay, so basically over here you can see that these are the general analog filter. This is actually the general digital filter. Okay, so basically from here you can see that this is actually the numbers of the order. Okay, so later on I will show you an example. Okay, so therefore for numerator, okay, they basically will determine the zero, while the denominator, they will determine the pole. With the pole and zero, they basically shape the filter response. Let me explain the second order transfer function of the filter. So from this transfer function, you can see that these are the transfer function for low pass filter, for band pass filter, and also for high pass filter. How I actually know that this is actually the second order? Okay, so basically from here you can see that this is actually the 2 here. So basically this actually state that this will be the second order. Okay, so the term second order actually refers to the fact that the transfer equation involve terms not higher than S2, as you can see from here. So hence, I will be able to know that this will be the second order transfer function. The second order transfer function actually describes two-pole filter. Third order transfer function, okay, S3 in fact will describe three-pole filter. Okay, so basically from here, okay, this actually describe two-pole filter. If it's third order, this will actually describe the third pole order. Okay, so the second order transfer function, in fact, will be a very useful starting point for us to understand better in terms of the filter design. Okay, because these are fundamental and hence the complex filter can in fact build out. So later on, I will study this second order transfer function for low pass. After that, I will go to high pass. And last but not least, I will go to band pass. But before I go in depth onto the discussion on the second order transfer function, I need your help, guys. I need your help by like this video. If later on or earlier on, if you have learned something from this video, urge you to support me by like this video and subscribe to this channel. Once again, thank you so much for strong support. Let me explain a little bit more on the three transfer function of low pass filter, band pass filter, and high pass filter. Firstly, okay, take note that they have the same denominator. From here, you can see that this is actually the denominator for low pass filter. This is for the band pass filter, denominator for the high pass filter. You can see that all three have the same denominator. Next, okay, observe the numerator. Okay, so basically they have the increasing power of S. Okay, so basically this is without S. So basically increased by one power. You can see that there is one S here. Another one increased by another power of S. So therefore you can see that this is actually the S squared. So this is what it means. Numerator have increased power of S. Okay, so please note that this equation represents the low pass, band pass, and high pass filter. Okay, you can also take note that this S, okay, basically is proportional to frequency. If you want, okay, you can actually replace this S with J radian. So from here, you can see that we can study the behavior of filter by breaking into 2 points. One is we call this radian equals to 0. This is what we know as low frequency. And when the radian is equals to infinite, this is what we know as high frequency. We can break this into 2 points to understand the characteristics of filter design. So let's say, for example, okay, when we actually put this radian equals to 0, okay, which is low frequency, into the equation of this low pass filter. Okay, so basically you put 0 here, you put 0 here. So the transfer function will be equals to K over A, as it mentioned over here, which means that you still have certain thing at the low frequency. Wow, the radian is equal to infinite, which means that at high frequency, again, imagine that this S can replace by J radian, and basically you can replace this radian with infinite here and another infinite here. Any number divided by infinite number, this will be very, very close to 0. So therefore, from here, you can see that the transfer function will be equal to 0. So what does this imply? This implies that at very low frequency, okay, basically when they are actually close to DC, okay, you can see that the transfer function has some function which is k over a over here. While for high frequency, okay, when this radian is equals to infinite, this in fact give h equals to 0, which means that nothing can be passed. So therefore, this equation actually indicate that this equation can only pass DC with a gain of k over a, and in fact they will attenuate infinite at high frequency. So in another word, this in fact actually describe a low pass filter. So basically, this is how we understand the transfer function of a low pass filter by determining the radian equals to 0 for low frequency and the radian equals to infinite for high frequency. Let me explain the transfer function for a high pass filter. Again, I'm going to break into two parts. Okay, firstly will be the radian equals to 0, which denote low frequency. Another part will be the radian equals to infinite, which is high frequency. Let's take a look on this high pass filter transfer function. As the radian is equals to 0, if you still remember, I told you that this S can be replaced by J radian. So when radian is equals to 0, you can see that the whole transfer function will be equals to 0, which means that low frequency cannot pass through this high pass filter. So next, okay, I'm going to study another characteristics, which is the radian is equals to infinite, which is high frequency. Okay, I can't use this formula anymore. Okay, I need to so-called rewrite this equation into this form here. Okay, so basically the numerator and the denominator of this high pass filter, okay, I need to divide them by s squared. Okay, so basically when I actually divide by s squared, this will be remain k. So basically this divided by s squared, this will be equals to 1. Okay, so b divided by s squared, I will have this s term over here. And basically this a divided by so-called s squared, okay, basically the j squared will become minus here. So this is actually another way to describe the equation. So now, okay, this w is equals to infinite, okay, which means that this is actually infinite. This is also infinite. So from here, you can see that infinite number minus infinite number, okay, I will replace this whole thing equals to 0. So therefore, you can see that my transfer function will be equals to a. So in simple word, you can say that basically this filter actually pass at high frequency and attenuate at low frequency. They actually pass with a value around k, while at low frequency, nothing is able to pass. So basically, this transfer function actually describes a high pass filter. Next, let me explain the transfer function of band pass filter. Okay, so this transfer function for band pass filter is slightly complicated. So therefore, I put it at the last one to describe this. Okay, so this is actually the frequency response of a band pass filter. So basically, this belongs to the low frequency. This belongs to the high frequency. In the middle, they actually allow them to pass. Let's take a look on these two extreme frequency, which I described earlier on. When this radian is equal to 0, okay, so basically you put this into the equation of band pass filter, you put a 0 over here. Okay, so when this is actually 0, you know that nothing can be passed over here. So basically at low frequency, everything will be attenuated away. So next, when W is equal to infinite, okay, so basically you put this into infinite. Over here, you can see that this is infinite square. So therefore, you can imagine that any number that divided by infinite square, this will be also a very small number. This means that at high frequency, again, there won't be any transfer function. Everything will go to 0. This is what you want to say. At radian equals to 0 or, and also at radian is equals to infinite, okay, the transfer function will be equals to 0, which I have explained earlier on. So next, let's take a look on a very special relationship. Okay, so basically the special relationship is when W is equals to A over W. Okay, so under this equation here, okay, which means that this equals to this, okay, which this is equal. Okay, so once they are equal, you can see that they actually cancel each other, and my transfer function will be equals to K over B. Okay, so basically under this special condition. Okay, when radian is equal to A over this radian here, okay, the H, which is the transfer function, will be equals to K over B. Okay, so this actually indicate that the equation will describe a filter that actually attenuate the low and high frequency, which I explained earlier on. They will attenuate at the low and also the high frequency, but they will pass the middle band, okay, with this characteristic K over B in another word. So therefore, this equation or this transfer function actually describe a band pass filter. Coming to my last slide for this video. Okay, so this above equation is meant for the transfer function for a low pass filter. In fact, you probably know that there are many different types of low pass filter. For example, we have the Butterworth, we also have the Chebyshev and the Bessel low pass filter. Okay, so the types of filter, okay, and also the shape of the response curve is basically determined by the constant A and B. As you can see from here, this A and B, okay, which is the equation for low pass filter, and the constant K, okay, which is a multiplier that will affect the filter gain. So basically, this A and B will determine the types of filter, whether it is Butterworth, Chebyshev, or Bessel low pass filter, while this constant K, okay, basically they will affect the filter gain. So the constant A and B, okay, in the above equation for band pass and high pass filter also determine the types of filter, and K again will be a multiplying factor that will affect the gain. So in short, low pass filter, high pass filter, and band pass filter, they will be the same. So the constant A and B, okay, they will be able to determine what types of filter it is. And based on this K, they will actually determine, okay, what gain the filter actually can be. So there are available table that is actually list the constant A and B for the various type of filter. Okay, so basically you can see that there are a lot of table for our design, whether it is Butterworth, Chebyshev, or Bessel function here. So in short, K is the scaling factor that is actually chosen by the design to give a specific gain. So typically, A and B are given as a coefficient in the polynomial function for various types of filter. With this, I'd like to end my discussion. Please help me to like this video and subscribe to this channel. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.